Now we're next going to take a look to see how the graph of y equals x squared compares to the graph of y equals 2x squared, the equation we're going to consider next. And what we've done here is to multiply the x squared by a constant whose absolute value is greater than 1. Now if we play again detective like we did with an earlier example, we can see that the y values for this graph will be twice as great as those for the graph of y equals x squared. So let's fill in the table, plot the points, and see what generalization we can make. Now what I've done is to sketch the graphs of both y equals x squared, which you can see is green, and the graph of y equals 2x squared, which is red. Now what do you notice? Hopefully you notice that the graph of y equals 2x squared is sort of skinnier or thinner than the graph of y equals x squared. And the way we describe that officially, mathematically, is to say that the graph of y equals 2x squared stretches the graph of y equals x squared by a factor of 2. So now we can determine the vertex, and I think you'll agree that the vertex will still be 0, 0. The axis of symmetry is the y-axis, which is x equals 0. Domain will be all reals. And the range will then be from 0 to infinity, because we can see that all the y values in the graph will be larger than 0, which is the y-coordinate of the vertex. So in general, if you multiply the x squared in the equation y equals x squared by a constant whose absolute value is greater than 1, then that will stretch then the graph vertically by a factor of whatever the constant is equal to. Now put on your thinking caps and make an educated guess about what you think the effect will have on the graph of y equals x squared if we multiply the x squared by a constant, in this case 1/2, whose absolute value is less than 1 but greater than 0. Now being the shrewd and intelligent observer that I'm sure you are, you noticed, I would imagine, that the y values for this graph will be exactly half the y values for the graph of y equals x squared for the same x values. And that's confirmed by the y values that you see in the table below. Now the question really is then, how will the graph of y equals 1/2 x squared then compare to the graph of y equals x squared? So let's graph both of them on the same set of axes and see what we have. Now you'll see the graph of y equals x squared is in green, and the graph of y equals 1/2 x squared is in red. Now what you notice is that the graph of y equals 1/2 x squared is in a sense fatter than the graph of y equals x squared. So we would say then, sort of in official mathematical terms, that the graph of y equals 1/2 x squared compresses the graph of y equals x squared by a factor of 1/2. Now from the graph we can easily determine that the vertex will be 0, 0. Axis of symmetry, still the y-axis, whose equation is x equals 0. Domain, all reals again. And the range, you can see, will then be from 0 to infinity. So in general, if you multiply the x squared by a constant whose absolute value is less than 1 but greater than 0, what that will do then is to compress the graph of y equals x squared by the factor of whatever the constant is equal to.